welcome to our channel. Today we're diving into the mesmerizing world of spectral lines. These lines, like cosmic fingerprints, hold the key to understanding the universe's most fundamental building blocks, atoms, and molecules. Hidden within starlight is a secret code, a language whispered by the cosmos itself. From the fiery heart of a distant star to the cool gas clouds where planets form, spectral lines allow us to decode the composition, temperature, and even the motion of celestial objects light years away. Let's embark on this cosmic journey and unlock the secrets hidden within these lines of light. Imagine an atom, a tiny nucleus surrounded by even tinier electrons, buzzing with energy. These electrons occupy specific energy levels like steps on a staircase. When an atom absorbs energy, its electrons get excited and jump to higher levels. Eventually, those excited electrons return to their more stable, lower energy levels. They release that excess energy in the form of a photon, a tiny packet of light. The energy of that emitted photon is directly related to the energy difference between the two levels the electron jumped between. These fingerprints are what we call emission lines, bright lines of color against a dark background, like cosmic neon signs announcing the presence of specific elements in the universe. Now let's flip the script and talk about absorption lines, the dark counterparts to the bright emission lines. Imagine starlight, a continuous spectrum of colors, traveling through a cloud of gas. As that light passes through, the atoms in the gas can absorb photons at specific wavelengths that match their unique energy level differences. Those absorbed photons are then missing from the continuous spectrum, leaving behind dark lines where they once were. These, my friends, are absorption lines. They are like shadows in the cosmic rainbow, revealing the composition of the gas cloud. Those missing colors tell us about the elements present in the material that absorbed them. So while emission lines are like the universe shouting its presence, absorption lines are more like cosmic whispers, subtly revealing the secrets hidden within interstellar clouds and stellar atmospheres. We've talked a lot about electrons jumping between energy levels, but what exactly are these levels and why are they so specific? This, my friends, is where the mind-bending world of quantum mechanics comes into play. In the quantum realm, energy isn't continuous, it's quantized, meaning it exists in discrete packets like tiny bundles of energy. And just like you can't stand between steps on a staircase, electrons can't exist between these quantized energy levels. These quantized energy levels are determined by the wave nature of electrons. In the quantum world, particles like electrons can also behave like waves. These stable energy levels are called quantum states, and each element has a unique set of these states, like a cosmic fingerprint determined by the number of protons in its nucleus. We've established that each element has a unique set of energy levels, but how do we actually measure these levels and decode this atomic fingerprint? The answer, my friends, lies in the very spectral lines we've been discussing. By carefully analyzing the wavelengths of light emitted or absorbed by an atom, we can determine the energy differences between its quantum states. By measuring the wavelengths of spectral lines, we're essentially measuring the energy differences between an atom's quantum states. These measurements are incredibly precise, allowing us to determine the energy levels of atoms with astonishing accuracy. This information is invaluable, not only for understanding the structure of atoms but also for identifying elements in distant stars and galaxies. Now let's delve into a specific example of spectral lines, the Balmer series in hydrogen. Hydrogen, the simplest and most abundant element in the universe, holds a special place in the history of spectral analysis. In the 19th century, a Swiss mathematician named Johann Balmer noticed a striking pattern in the visible spectrum of hydrogen. He observed a series of lines now known as the Balmer series, with decreasing spacing as they approached the violet end of the spectrum. Balmer ingeniously devised a mathematical formula that accurately predicted the wavelengths of these lines. The Balmer series arises from electron transitions in hydrogen atoms, where the electron falls to the second energy level, also known as the n equals 2 level. The Balmer series was a crucial stepping stone in the development of quantum mechanics, demonstrating that the energy levels in atoms are indeed quantized and paving the way for our modern understanding of atomic structure. Now, let's venture into the realm of forbidden lines, spectral lines that are rarely observed in laboratory settings but can be prominent in the vast expanse of space. These lines, my friends, aren't actually forbidden. They're just highly improbable under typical laboratory conditions. Some electron transitions are more likely to occur than others. These allowed transitions produce the bright and easily observable spectral lines we've discussed. However, there are also forbidden transitions that are much less likely, making them difficult to produce in a lab. In the vast, low-density environments of space, like the diffuse gas clouds called H2 regions, atoms can remain in excited states for much longer times than on Earth. This extended lifespan allows even these forbidden transitions to occur, producing faint but detectable spectral lines. Now let's turn our attention to our very own star, the Sun, and the fascinating story of Fraunhofer lines. In the early 19th century, a German physicist named Joseph von Fraunhofer made a groundbreaking observation while studying the Sun's spectrum. He noticed that the Sun's otherwise continuous spectrum was crisscrossed by hundreds of dark lines, like tiny imperfections in the rainbow. These lines, now known as Fraunhofer lines, were initially a mystery, but they held the key to unlocking the Sun's composition. Fraunhofer meticulously catalogued these dark lines, assigning letters to the most prominent ones. These dark lines are absorption lines, formed as sunlight passes through the Sun's outer atmosphere. By carefully analyzing the wavelengths of these Fraunhofer lines, astronomers could identify the elements present in the Sun's atmosphere, revealing its composition and forever changing our understanding of our nearest star. As we delve deeper into the world of spectral lines, we encounter a fundamental constant that plays a crucial role in determining the wavelengths of these lines, the Rydberg constant. This constant, named after Swedish physicist Johann Rydberg, is a cornerstone of atomic physics. The Rydberg constant appears in the formulas that describe the wavelengths of spectral lines, particularly for hydrogen and hydrogen-like atoms, which are atoms with only one electron. It essentially sets the scale for the spacing between energy levels in these atoms. The Rydberg constant connects the energy levels of atoms to the wavelengths of light they interact with, establishing a bridge between the quantum world and the macroscopic world we observe. Now let's talk about a fundamental equation that connects the energy of a photon to its frequency, E equals hn. This deceptively simple equation where E represents energy, h is Planck's constant, and nu is the frequency of light, has revolutionized our understanding of the relationship between light and matter. This equation tells us that the energy of a photon is directly proportional to its frequency. By measuring the frequency or wavelength of a spectral line, we can directly calculate the energy difference between the two quantum states involved in the transition using this equation. This equation, my friends, is a cornerstone of quantum mechanics and has profound implications for our understanding of the nature of light and its interaction with matter. As we've explored the world of spectral lines, you've likely noticed that these lines often appear in groups or series. These spectral line series, my friends, are not random occurrences. They arise from the quantized nature of atomic energy levels and the specific rules governing electron transitions. Each series corresponds to a set of electron transitions where the electron falls to a specific energy level. For example, the Balmer series in hydrogen, which we discussed earlier, corresponds to transitions where the electron falls to the En equals 2 energy level. Other series, like the Lyman series, Paschen series, and Brackett series in hydrogen, correspond to electron transitions to the N equals 1, N equals 3, and N equals 4 levels, respectively. These spectral line series provide a powerful tool for astronomers to identify elements in distant objects. Thanks for watching. If you enjoyed this deep dive into spectral lines, don't forget to like, subscribe, and hit the bell icon for more fascinating science content. We've journeyed from the quantum realm of atoms to the vast expanse of space, unraveling the secrets hidden within these lines of light. Remember, spectral lines are more than just lines on a spectrum. They are cosmic fingerprints revealing the composition, temperature, and motion of celestial objects across the universe. Keep exploring the cosmos, my friends, and never stop questioning the universe around us. Who knows what other secrets await to be discovered? See you next time.